Have you ever wondered what holds things together? Or what makes a battery work? The answer often involves tiny charged particles called ions. They are invisible to the naked eye, yet fundamental to the workings of the universe. From the salt on your table to the stars in the sky, ions shape our world. They are the unsung heroes of chemistry and physics. This journey will explore these fascinating entities. We will discover what ions are, how they come to be, and why they are so important. Think of this as your personal guided tour into a realm often unseen but always present. We will keep things simple and use everyday language. Understanding the universe, even its smallest parts, should be accessible to everyone. Imagine a world without ions. Many chemical reactions would simply not occur. Life as we know it might not exist. The very fabric of materials would change. Ions are that crucial. They drive processes in nature and technology. They are the movers and shakers at the atomic scale. So let's embark on this adventure together. Let us reveal the simple elegance of ions. By the end, you'll see the world differently. You'll appreciate the subtle, powerful forces that ions exert. Let the exploration begin. To understand ions, we must first journey into the atom. Think of an atom as a tiny solar system. It is the fundamental building block of all matter. Everything you see, everything you touch is made of atoms. For a long time, humans thought atoms were the smallest things. But we now know they have an inner structure. At the very center of this atomic solar system lies the nucleus. The nucleus is like the sun, small, dense, and packed with power. Inside the nucleus, we find protons and neutrons. Protons carry a positive electrical charge. The number of protons defines what element an atom is. Alongside the protons in the nucleus are neutrons, which are neutral. Neutrons help hold the nucleus together. The nucleus is a dense core of positive protons and neutral neutrons. This core contains almost all the mass of the atom. Orbiting the nucleus, much like planets around a sun, are electrons. Electrons are tiny particles carrying a negative electrical charge. In a neutral atom, the number of electrons equals the number of protons. This balance means the atom as a whole has no net electrical charge. It is this delicate balance that gets disturbed when an ion is born. The story of ions unfolds with the atom's electrons. Their gain or loss is what turns a neutral atom into a charged ion. This transformation opens up a new world of chemical possibilities. Understanding this miniature universe is key to grasping the concept of ions. So, let's dive deeper into the world of charged particles. The journey continues. Atoms, in their natural state, are typically neutral. They possess an equal number of positive protons and negative electrons. This balance is like a perfectly weighted scale. But atoms are dynamic and can interact. During these interactions, they can gain or lose electrons. This is the essence of ion formation. If an atom loses electrons, the balance is broken. The number of positive protons now exceeds the number of negative electrons. The atom becomes a positively charged ion. Conversely, an atom can gain electrons. If it gains extra electrons, the balance is again broken. The number of negative electrons becomes greater than the number of positive protons. The atom becomes a negatively charged ion. During this transformation, the nucleus remains unchanged. The number of protons and neutrons stays the same. This means the element itself does not change. A sodium atom that becomes an ion is still sodium. It just has a different electrical charge. It's the electrons that are involved in this electrifying dance. Their gain or loss turns a neutral atom into a charged ion. This opens up a new world of chemical possibilities. Understanding this process is key to appreciating the role of ions. Let's explore further. When an atom loses electrons, it becomes positively charged. These positively charged ions are called cations. Think of the T in cation as a plus sign to remember they are positive. Metals, for example, tend to lose electrons easily. Consider sodium, a soft silvery metal. A sodium atom has 11 protons and 11 electrons. It's relatively easy for a sodium atom to lose one electron. When it does, it becomes a sodium ion, written as Na+. This ion is much more stable than a lone sodium atom. The magnitude of the positive charge on a cation depends on how many electrons are lost. For example, a calcium atom commonly loses 2 electrons to become a calcium ion, written as K2+. Similarly, aluminum often loses 3 electrons to form Al3+. These charges dictate how these ions interact with other particles. Cations are everywhere. Sodium ions, Na+, and potassium ions, K+, are vital for nerve function in your body. Calcium ions, Ca2+, are crucial for strong bones and teeth. Magnesium ions, Mg2+, are important in many enzymes and in chlorophyll. These positive powerhouses play diverse and critical roles. Their positive charge allows them to engage in a multitude of chemical interactions. Let's move on to their counterparts. Now let's turn our attention to the other side of the ion story. When an atom gains electrons, it becomes negatively charged. These negatively charged ions are called anions. You can think of the N in anion as standing for a negative ion. Anions have more electrons than protons. The extra negative charge tips the balance, giving the ion an overall negative charge. Some atoms, particularly nonmetals, have a strong attraction for electrons. Consider chlorine, a greenish-yellow gas. A chlorine atom has 17 protons and 17 electrons. It has a strong tendency to gain one electron, becoming a chloride ion, written as Cl. The magnitude of the negative charge on an anion depends on how many electrons are gained. For example, an oxygen atom commonly gains 2 electrons to become an oxide ion, written as O2. Anions are just as important as cations. Chloride ions, Cl, are essential components of table salt. Fluoride ions, F, help prevent tooth decay. Oxide ions, O2, are fundamental components of many minerals and materials. These negative ninjas contribute significantly to the structure and function of the world around us. Let's see how they interact with cations. Now that we understand cations and anions, we can explore how they interact. Opposites attract. A positively charged cation and a negatively charged anion will feel a strong electrostatic attraction. This attraction can be so strong that it holds the ions together, forming an ionic bond. Think of it as a cosmic handshake. Consider the sodium ion, Na+, and the chloride ion, Cli. Sodium loses an electron to become Na+. Chlorine gains an electron to become Cli. When these two ions come near each other, they form an ionic bond, creating sodium chloride, NaCl. You know this compound very well, it's common table salt. Ionic bonds don't just form between two individual ions. In a substance like salt, many cations and anions come together in a crystal lattice. This structure gives ionic compounds their characteristic properties. The formation of ionic bonds leads to the creation of ionic compounds. These compounds are made up of ions, not neutral atoms. Water can dissolve many ionic compounds. When salt dissolves in water, the Na+ and Cl ions separate and become surrounded by water molecules. The cosmic handshake can be temporarily loosened, allowing ions to move and do work. It's crucial to appreciate the profound differences between a neutral atom and its corresponding ion. They might share the same nucleus, but their personalities are worlds apart. A neutral atom has an equal number of protons and electrons. It carries no net electrical charge. An ion, however, has either lost or gained electrons. This means it carries a net positive or negative electrical charge. Consider sodium again. A neutral sodium atom, Na, is a highly reactive metal. If you drop a piece of sodium metal into water, it reacts violently. Now think about the sodium ion, Na+. This ion has already lost that electron. It has achieved a stable electron configuration. The sodium ion is remarkably stable and unreactive compared to the sodium atom. The transformation from a reactive metal atom to a stable, life-sustaining ion is truly astonishing. This difference in reactivity and properties is a general theme. An ion is not just a charged atom, it's a new chemical species with its own distinct character and role in the universe. Let's see ions in action. The world of ions isn't confined to chemistry labs or abstract theories. Ions are constantly at work all around us, and even within us, performing everyday miracles. Your ability to read these words, to think, to move, relies heavily on ions. Nerve cells in your brain and body use ions like sodium, Na+, potassium, K+, and calcium, Ca2+, to transmit electrical signals. Consider the batteries that power your devices. Batteries rely on the movement of ions. Inside a battery, chemical reactions produce a flow of electrons, which is electricity, and involve the movement of ions between the battery's electrodes. For example, lithium-ion batteries use lithium ions, Li+, that shuttle back and forth as the battery charges and discharges. Ions also play a critical role in something as fundamental as water. Pure water doesn't conduct electricity very well, but when ionic compounds dissolve in water, they release ions. These ions can carry an electrical current, making the water conductive. Electrolytes in sports drinks are essentially salts that replenish ions lost through sweat. Even the vibrant colors of fireworks are due to ions. When metallic salts are heated in a firework, the metal ions emit light of specific colors. Strontium ions create red, barium ions create green, and copper ions create blue. From the silent signals in your brain to the explosive beauty of fireworks, ions are truly performing miracles all around us. Let's conclude our journey. We have journeyed into the realm of the very small. We have explored the atom and its transformation into a charged particle, the ion. Ions are fundamental players in the grand theater of the universe. An atom becomes an ion by either losing electrons, resulting in a positively charged cation, or by gaining electrons, forming a negatively charged anion. This simple exchange of tiny electrons unlocks a vast array of properties and possibilities. These charged particles are driven by electrostatic attraction. Oppositely charged ions attract each other, forming powerful ionic bonds. The difference between a neutral atom and its ion can be stark, transforming a reactive element into a stable component. The significance of ions extends far beyond the formation of compounds. They are the lifeblood of biological systems, enabling nerve impulses and muscle contractions. They power our technologies. From the batteries in our pockets to industrial processes, ions are the invisible architects, the tireless workers, the silent messengers. They are truly ubiquitous and essential. So, the next time you sprinkle salt on your food or use your phone or simply take a breath, remember the ions. The universe, both within us and around us, is a charged universe. Understanding ions gives us a deeper appreciation for the fundamental forces and particles that govern everything.